Hello, algebra students. This lesson is going to be all about graphs that represent situations. This is a really exciting lesson because it is our final lesson in our unit on quadratics and also our final lesson for Algebra 1B. I also really like this lesson because there's not really any new math skills in this lesson. It's just all about applying all of the different things we have learned in this unit to some of these quadratic situations we've looked at. Starting with our warm-up, this story in our warm-up is story 1 of the 3 that we are going to be looking at in this lesson. Go ahead, pause the video now, try answering questions 1 and 2, and come back when you've got some answers. I am going to go to the next slide just to make it a little bigger. The story was about a frog that jumps. So we've got the height in inches of a frog's jump is modeled by the equation h of t equals 60t minus 75t squared, where time is represented with t. The time after it jumps is represented by t, and it's measured in seconds. The first question is asking us to find h of 0 and h of 0.8. So let's start with that. To find h of 0, that just means t is 0. So we are substituting in the number 0. That's going to be 60 times 0 minus 75 times 0 squared. When we go to do that math, that is 0 minus 75 times 0. 75 times 0 is 0, so we just get 0 minus 0. That is 0. So h of 0 equals 0. We'll do that one more time with 0.8. H of 0.8, we're going to do the same thing. We're substituting in 0.8 for t. Minus 75 times 0.8 squared. 60 times 0.8 is going to be 48. Minus 75 times 0.8 squared. 0.8 times 0.8, that's 0.64. And then 75 times 0.64 is 48. And so we get 0. H of 0.8 equals 0. So we've gone ahead and we found both of them. What do they mean in terms of the frog's jump? Well, t represents our time, and h of t represents the height. So when I'm looking at this, t of 0 means 0 is my time, 0 seconds. And when I get h of 0 equals 0, that means this 0 here represents the height. So this one is saying at 0 seconds, or at the start, the frog's height is 0. And at 0.8 seconds, the frog's height is 0. So we've got it's 0, it's on the ground, the height is 0 at 0 seconds and 0.8 seconds. Number 2 asks the question, how much time after it jumped did the frog reach the maximum height? Now, I've had students read through this and say, it would sure be nice if we have a graph. Am I supposed to graph it? We can start thinking about the graph, but it's not necessary to have the graph to answer this question. If we think about the graph, down here is our time, our seconds, and this is our height. We already know 2 points. We know that we have a point here at 0, 0. 0 seconds, the height is 0. And we also know at 0.8, the frog is on the ground. So what happened in between this time? The frog jumped. The story is about a frog jumping, right? We've just got this first 0 here is the start of the jump, and then the frog must have jumped. And 0.8 seconds is when the frog landed. So if I'm asking you what time is the frog at the maximum height, think about what we know about graphs of parabolas. Where would the maximum height be? Well, in this graph, the maximum height is our vertex. We said our vertex is our highest or lowest point, and because of the way frogs jump, right, it's going to start by increasing, then decreasing. Our vertex would be right here. And there's something else we've learned about the vertex. We have learned the vertex is always in the middle of your x-intercepts. And that's what this 0 and 0.8 is. So when is the frog at its highest point? It's at its point halfway through this jump which would be at 0.4 seconds. I know that because it's halfway through the jump. I could have also asked you at what height is it at its maximum height? And we could do that the same way we did these first two by substituting in the time 0.4 seconds, and that would tell us how high that frog got to. This question's not asking for that though, it's just asking for the time. And so we're using the fact that the vertex is halfway between those x-intercepts to help us answer that. Like I said at the beginning of this lesson, none of this math we are doing here is new. I've had you substitute numbers into equations before. We've talked about the vertex being halfway between our x-intercepts before. The new idea in this lesson is just using all of this to help us analyze situations, like this one about a jumping frog. We've talked a lot about where on the graph and which points are going to be those essential points. And we've talked about them as kind of like a set of three different things: your x-intercepts, your y-intercept, and that vertex. When you're talking about quadratic graphs, those are the essential parts. And so we're noticing here those x-intercepts are telling us in this situation when the frog was on the ground, and that vertex is telling us that maximum height there. We've got two other situations that are going to have us think about those same key important points on our graph and what they mean in terms of different stories. So the theme of this lesson is examining graphs that represent the paths of objects being launched into the air. Earlier on in this unit, we had these whole lessons on looking at quadratic situations like throwing objects or dropping objects. We are revisiting those stories, but now we are so much wiser and we know so much more about quadratic situations. Our second story we're going to be looking at is about a catapulted pumpkin. A catapulted pumpkin is using a catapult. It's that tool or that machine that launches objects into the air. I think in the past it was used for like wars and fights, but here we are catapulting a pumpkin. You can find videos of these online if you want a visual of what this means, but just know that we are launching a pumpkin into the air. We are given this equation here that represents the height of the pumpkin as it is catapulted up into the air as a function of time t in seconds. The height is measured in meters above the ground, and the pumpkin is shot up at a vertical velocity of 23.7 meters per second. There are 4 questions up here on the screen. Again, we've been saying, none of the math is new, so you could be able to answer all of these questions using what we've learned in previous lessons. So I strongly encourage you to pause the video now and see what you remember from past lessons about quadratic equations, and then come back to get the answers. The first question is talking about what these numbers in this equation means. This goes back to this exact lesson we had done on stories of quadratic situations like throwing objects. And in that lesson, we had talked about what each part in your quadratic equation represents. This 2 right here, your constant, represents where that object is starting. So in this situation, the 2 tells me that the pumpkin starts from a height of 2, we're measuring in meters. So I can say the pumpkin starts at 2 meters, I'm going to say above ground. That's our starting height right there. That should make sense because if you're putting a pumpkin in a catapult, it's not going to be on the ground. So it's starting at 2 meters. That's about 6 feet above the ground. The negative 4.9 t squared, what does that represent? Well, we had talked about in that lesson where you're launching objects into the air and dropping objects, that quadratic term, the term with t squared, always is representing, do you remember it? The effect of gravity. It's negative because gravity is what is bringing our pumpkin back down to Earth. There is one other term in that equation at 23.7t, and our story already tells us what that represents. That's representing the velocity or the speed that pumpkin is going vertically up into the air. The second question asks, if we were to graph this equation, would it face upward or downward, and why? How do you know? You can think about what a pumpkin looks like as it's flying through the air, or you can think about what we learned in the previous lesson. In the previous lesson, we were talking about graphs of standard form, and we learned that if this quadratic term here, that negative 4.9t squared, we learned if that term is negative, it means it is facing downward. That means our pumpkin is going to fly up into the air and then come back down, and our parabola is facing downward. Downward just means those arrows are facing down. Why? How do I know that? I know that because of that negative 4.9t squared. If that term was positive, it would mean it's facing upward. The third question, where do you think the vertical intercept would be? Remember vertical intercept? The vertical is lines going this way, so it's like your y-intercept. Where would that vertical intercept or your y-intercept be? Well, the vertical intercept would be where the height is starting. And we've already talked about that. Our height is starting at 2. In our last lesson on graphs of standard form, we also had talked about how your constant right here, this 2, always represents that vertical intercept or your y-intercept. So it would be at 2. I'm going to go ahead and write it as a point. 2 is the y-intercept, so 2 would be my y value, and then we've got 0 here. This literally is saying at 0 seconds at the starting point, the height is 2. The height is 2 meters. Finally, for our horizontal intercepts, what do we know about horizontal intercepts? Or those are the same thing as x-intercepts. Well, we've been saying that for your horizontal intercepts, it is helpful to have factored form. Vertical intercepts or y-intercept, you want standard form. X-intercepts, horizontal intercepts, you want factored form. And so based on what I have so far, I don't know that. For this, I'm going to just write I need factored form. I need factored form, or I need the graph. If I had the graph, I could figure that out too. But based on what I've got here, I don't have enough information to know where those horizontal intercepts are. In the next part, we are going to go ahead and we are actually going to graph the equation from this story. And using that graph, we are going to identify the vertical and horizontal intercepts as well as the vertex of the graph. We didn't talk about that in the previous question, but we'll identify that as well. And so switching us over to Desmos, I went ahead and I graphed it for us on Desmos, and here is our graph. So we had said we were going to identify the intercepts and the vertex. I'm going to go ahead and start with our vertical intercept or our y-intercept. And there it is. We said this earlier, but it is at 0, 2. Means we are starting off at a height of 2 meters. Now that we have the graph in front of us, we can also find the x-intercepts. We've got one right here at negative 0.083, and we've got one here at 4.92. Let's talk about those x-intercepts. What do those mean in this situation? Well, similar to what we had said about our y-intercept, that first number represents our time, and the second number represents our height. It makes me kind of think of the frog problem. These are the 2 times where the height is 0, which means the pumpkin is on the ground. Now, when I'm looking at these, only one of these makes sense to me. I can have a time of 4.92 seconds, 4.92 seconds after the pumpkin is launched or catapulted, it lands on the ground. But this other one, that negative 0.083, that one doesn't make sense to me. You cannot have negative 0.083 seconds. You can't have negative seconds. And so an important thing to keep in mind is technology is great. It can make these graphs for us, but we're still using our brain to analyze them. I have to understand that the website's going to give me the whole graph, but I'm really only focusing on this graph from this y-intercept here until that x-intercept. Anything down here, these are negative heights. That means that pumpkin is going underground. And then anything over here, these are negative heights as well as negative times, and those don't make sense. There's one final point we said we were going to look at, and that is our vertex. Where is the vertex? Well, it is our highest point, and I'm going to find it in between our x-intercepts. So if I go to the middle of our parabola, here it is. We've got some crazy numbers we're looking at. What do each of those numbers mean? Well, the first number is the time, so at 2.418 seconds, we'll just say 2.4 seconds. What's this 30? That is the height of our pumpkin. So at 2.4 seconds, our pumpkin is at a height of 30.658 meters. That is quite high. That is almost 100 feet up in the air. So our vertex is special because it's telling us that maximum height of the pumpkin. It is the highest point on this graph, and it is also the highest point the pumpkin reaches. Again, I want you to notice the 3 points we focus in on as we're doing this analysis are your intercepts, your x-intercept, your y-intercept, and your vertex. Those are going to be the points that tell you the most information about the story. We have one final question we're going to be looking at. Here, I like this question because you are going to be using everything you know to compare two situations. And so for this story here, it's going to be us comparing the flight of two baseballs. We've got the first question here on the screen. Go ahead, pause the video here and try this now. So in this story, we have two different players. Player A's baseball is represented by this graph. Player B's baseball, we don't have a graph. Instead, we have this equation here. The question we are answering is which player's baseball stayed in flight longer? And the key to answering that question is figuring out what feature are we trying to identify to help us answer this. We've been talking about three, right? The y-intercept, the x-intercept, or the vertex. Which one is going to help me answer this? Well, if we want to know how long the baseball has stayed in flight, I'm going to think about some of the other situations we've looked at. For our frog, for example, if I asked you how long was the frog in the air, those x-intercepts are what tell me that. It was in the air from 0 seconds to 0.8 seconds. That's letting me know how long our frog was in the air. And it's going to be the same thing down here. To know which baseball is in the air longer, I need to focus in on our x-intercepts. For the graph, that's a little easier. I'm just going to my x-axis, and I see we've got an x-intercept right here. It looks like it's a little after 5. And so player A's baseball was in the air for a little more than 5 seconds. For this equation here, I don't have a graph, so I have to use what I know about quadratic equations. If I wanted to find the x-intercepts of this equation, what do I need to do? Well, it's in factored form, and that's perfect for x-intercepts. We just need to set each part of this equal to 0. So I'm solving negative 16t minus 1 equals 0, and I'm solving t minus 4 equals 0. If you solve this one, you get an answer that does not make sense. I'm going to have a negative time, t equals negative 1/16. But if I solve this one, it's also the easier one to solve. We get t equals 4. So that means the second player's baseball landed on the ground at 4 seconds. So we can see between those two which player's baseball stayed in flight longer. It is going to be player A. You know, so many times we're asked to explain how we know. I could explain how I know by saying I looked at the x-intercepts. Player A's ball landed after 5 seconds, and player B's ball landed after 4 seconds. Jumping to the next question here. Same story about player A and player B's baseball. This time I'm asking you which player's baseball reached a greater maximum height. Again, pause the video here, see if you can use all of this wonderful quadratic graph information we've learned to help you answer number 2. For number 2, just like with number 1, the key here is identifying what feature are we looking at. If I'm asking you about the greater maximum height, which part of your quadratic function is going to tell you that? If we're talking about the maximum height, that means we are using vertex. So looking at our graph here, that vertex is going to be the highest point on our graph, and that looks like it is around here. The question's asking which one is at a greater maximum height. So I can see it looks like around 2.5 seconds. Its height is, it's well over 100 feet. I'm going to go ahead and I'm going to estimate about 105 feet. So we've got our first graph here is getting to a maximum height of 105 feet. For our second one, how do we find the vertex from factored form? Well, it is going to require us using those previous answers. So remember, we had those two intercepts. We had one at 4, and then the other one was at negative 1/16. Negative 1/16 is about 0.06. If we were trying to be super, super accurate, I would use this number to save us time, though, and because I know the answer and it's not going to make too much of a difference, I'm just going to use x-intercept at 0 to help us there. It's very, very close to 0.06. I promise it won't mess with our answer. We said that the vertex is always halfway between your x-intercepts. So if we've got our x-intercepts at 4 and really, really close to 0, we know our vertex is halfway between those. Our vertex I would find at a time of 2. Similar to what we were seeing here, how it's really close to 5, and we said that vertex is about halfway. It's about 2.5. Halfway between this would be around 2 seconds. To find the height, how do I use 2 seconds to help me find the height? Well, we're going to substitute a time of 2 into this equation. So I'm solving for time of 2. That means I need to do negative 16 times 2 minus 1, and then times 2 minus 4. Negative 16 times 2 is negative 32 minus 1. I'm going to go ahead and say 2 minus 4 is negative 2. Negative 32 minus 1 is negative 33. And negative 33 times negative 2 gives me 66. So what we are learning is our second baseball, player 2's baseball, gets to its highest point at 2 seconds, and that highest point is 66 feet. We have enough information now to answer the question, which player's baseball reached a greater maximum heights? That is going to be player A's. It got to a height of 105 feet, whereas player B's baseball only got to about 66 feet. There is one final question of this final problem of this final lesson, and here it is. The question number 3 says, how can you find the height at which each baseball was hit? Go ahead one last time, pause the video here, try to answer number 3, and then come back to see how you did. We've said the key for each of these problems is to identify what feature we are going to use to help us answer this question. The first problem, when I was asking you which one stayed in the air longer, we were looking at the x-intercepts. Here, when I was asking about maximum height, we were using the vertex. And here, if I'm asking about where the baseball was hit, that's asking about where the baseball is starting at what heights, and that is all about your y-intercepts. So one last time, we'll start with this first graph. If I asked you to identify the y-intercept, just like with our x-intercept, we're going to have to do some estimating here. My y-intercept is right here, and I'm going to guess that it looks like it's around 5. And so based on this first graph, we can say player A's baseball was hit from a height around 5 feet. How am I finding that height? I'm looking at the y-intercept of the graph. Now, if I want the y-intercept for this equation, what am I going to need to do? Well, we said earlier, this equation is in factored form, which was super helpful for finding our x-intercepts. But if I want to know the y-intercept, what am I going to have to do with this equation? I have to change it to standard form. And so to do that, we are going to multiply this out. I'm going to go ahead and start by distributing negative 16t to t. That's negative 16t squared. Negative 16 times negative 4 gives me a positive 64. And then the same thing with the negative 1. Oh, I'm missing something on that 64. 64t. And then our negative, I'm trying to change color. Negative 1 times t is negative 1t, or just negative t. And then negative 1 times negative 4 is positive 4. You can go ahead and simplify this. We do already know the answer. But if you simplify this, you get 63t plus 4. I said earlier we already know the answer because I'm really just focused on y-intercept. And where is the y-intercept? It is our constant. So as soon as you got that plus 4 up here, you could have stopped. I know that the second baseball, by changing it into standard form, it shows me that the y-intercept is 4, and the baseball was hit from a height of 4 feet. We weren't asked to do any comparing here really. I think it would be really hard unless we had an exact point here, because I estimated 5, but maybe it's 4, maybe it's 6. It's hard to know without actually having that specific point labeled for us. But the idea, how could you find the height it's hit at? We're looking at that y-intercept. This is it. We have finished this last lesson, and we have finished everything there is to learn in our Algebra 1B class. That's super exciting. I hope you are proud of yourself and everything you've learned in the class this quarter. And thank you so much for watching this video.